So with that, I'm going to welcome Rob Farber. Rob has worked in the field since the obsession of backpropagation at Los Alamos Labs. He's on staff at Berkeley, has spawned 2 companies that have achieved liquidity events using artificial intelligence, and has worked in the field since. Can you please join me in welcoming Rob to the floor and to present to us.
Thank you very much. Well, this is my first time in Australia, and I have to say that Perth is absolutely gorgeous. You have a lovely, lovely city here. And I was thrilled to see that, being from Washington State, that the home of Costco, that you're actually getting a Costco warehouse here in about a year, so that makes life good. And had an unusual experience riding down in the lift. Someone asked me where my accent was from, which is unusual for an American, so that was quite good. I'm looking forward to spending some additional time, but I understand that, being from the Puget Sound area, which is famous for a lot of rain, that you're bringing in a lot of rain on my behalf. Please don't do that. I want to stay with the nice, boring weather. So I need to start up my presentation, which is here. And slideshow. So I've been very lucky in my career. I've been able to speak and teach around the world. This is a little bit of a brag slide. Am I whistling? A little bit of a brag slide on the number of locations around the world that I've been able to speak at. And I was very happy to add a new star down here in Perth. So the idea behind this talk is that AI is impacting everything in the HPC community. And as the first presenter, I'd like to start out with kind of a cartoon, giving a little bit of a background. And that is that we're kind of in this current state of the industry because GPUs have essentially accelerated machine learning and brought the technology into a forefront. I started working in the area in 1984, where we're using the connection machine, which is kind of one of the first early memory GPUs. And basically, when NVIDIA came out with CUDA, that it was going back and forth as far as the gaming market, which is a multi-billion-dollar market. Then NVIDIA came up with the great idea that you could actually do programming, and they came up with CUDA. ATI responded saying, no, we can use a programming framework called OpenCL. NVIDIA said, yeah, we can do that too, but you really want to work with CUDA. And the industry continued on, and sales started happening. The Intel giant really didn't pay attention to what was going on. Sales started happening. Let's hope that this works again, unless I somehow turn the thing off. And please work. Oh, no. OK. Anyways, sales started happening, and the Intel giant started ignoring it until sales reached 500 million GPUs. And then they went, well, that's a big enough market to attract us. So then they woke up and they came out with a variety of different frameworks which have changed and evolved over the years. And now the current one is Intel Scalable. So now we're sort of in a situation in the HPC community where we have GPU camps and CPU camps. And thank you for inviting me here, because I am a little bit of a heretic, because I point out that CPUs are also good for doing AI now. It basically boils down to memory bandwidth. And as long as you have enough computational throughput to maximize the memory bandwidth, that's going to be your peak performance, whether you're doing machine learning or other technology. So here's kind of a look into where the CPU roadmap is going. And we'll investigate this a bit further. But basically, we've got a number of new technologies, a new set of architectures, including non-von Neumann architectures, which I'll talk about in a little bit, that are changing the industry. So we're on the second bandwagon for machine learning AI. Basically, the field started out with something called an electronic brain, which I don't know much about. And then it worked into perceptrons, which use basically lines to try and fit data sets. Well, I'm grateful to Minsky and Papert, because they pointed out that there were a large number of problems that could not be solved with perceptrons, which basically stopped the field. What they did is they showed that you could not solve the exclusive OR problem, which is a nonlinear problem. And I'll talk a little bit more about that. And there was essentially an AI desert for a while. There was just no progress. About the time I joined the theoretical division at Los Alamos, there was some new work coming out where you could actually use nonlinear systems to do solutions to problems like the traveling salesman problem. And backpropagation came out about that time. And that really helped me. My colleague Alan Lapidus and I, we've got about 45 papers from around this era. Yes, I'm getting older, showing how work happens. So I'll talk about the first AI bandwagon, giving a little bit of a historical, personal perspective on this, and then move into the new technologies. But I think it's important to understand some of the capabilities that we already have. So why is XOR such an important problem? Well, it's nonlinear. Basically, if you can't solve the XOR, you can't train up a neural network to solve the XOR problem, which has 4 inputs and 4 examples, then you can't come up and configure all the gates that are used for a digital computer, which is a computationally universal Turing device. And so there are classes of problems you can't solve. And that's what killed the field. Well, it turns out that Romahart showed that you could actually solve XOR, and there's a pattern here. And the important pattern is that they use something called a sigmoid. So remember I was talking about the perceptrons, which just use a straight line, okay? So you were dividing up the data into hyperplanes. Turns out that real neurons don't respond very well if you give them too small of an input. And they also saturate. They don't respond very well if you give them too much input as well. And then there's a linear region. So the first pattern I like to point out is every time we do something that Mother Nature is doing in mammalian brains, we get a big jump in capability in machine learning. So in one of the finest examples I've seen of both science and also scientific showmanship, but I don't mean it showmanship as someone who is being able to show information, but rather in the sense of being able to clearly convey a very complex concept very quickly and intuitively to an audience. A friend and colleague, Terry Snowski, came up with NetTalk, where he essentially trained up a neural network to read aloud. And what he did is he stopped the network partway through the training process. He showed it essentially English text and the phoneme that should be pronounced for the center letter. And here's what he got. Doesn't sound like anything. In fact, Terry found out that he had to use a child's voice because it unsettled the audiences when he used a grown-up voice, kind of speaking blather. But where you really get the audience is when you train it to finding the global minimum.
I like to go to my grandmother's house. Well, because she gave us candy.
By the way, that example works well in the 6th to 12th grade class. So basically what Terry showed is that the neural network could learn a very, very complex task from a small set of data. The cool part is that you could show it words it had never seen before and it would pronounce them correctly. So he got across the ideas of complex learning, of difficult task, and the ability to do generalization in one simple audio example. So I use that in my classes to teach why the ability to communicate concepts to an audience is as important as coming up with the concepts themselves when you're teaching young scientists. So 2 points right now. First is every time we model essentially what Mother Nature does, we get a big improvement. And secondly is learn to communicate your ideas. So Alan Lapidus and I said, well, if we can do that with English text, let's show it on DNA and start predicting coding regions in DNA, which we did. And this is where we started running on the connection machine and came up with a very efficient mapping that we now use. But we go from the connection machine to here's the latest architecture for a TU-102 GPU. Massive parallelism. And at the time, the connection machine cost $30 million. About 2013, you could get a teraflop of performance from a system for about 1 to 3K. And CPUs at that time were really lagging because memory bandwidth. They just didn't have enough oomph to feed the processing units. So there's the teraflop line. Here's an example running on 16,384 GPUs because essentially, I'll show you the scaling, but machine learning, we can scale to as many distributed nodes as we want as long as we've got a sufficient communications network. So this is 13 petaflops average sustained performance on the Oak Ridge Titan supercomputer. So we can train basically on as large data sets as we can get. and as big as we want with backpropagation. The way we do this is a really simple method. It's a data parallel method. And basically what we do is we use some numerical optimization method, like Powell's method. The best at this point in time that I've seen is the LBFGS training. But basically everything fits underneath here through these 3 steps. And the first step is that we broadcast the data to all the processing units. Well, that's a constant time operation. Think of the television model. You can broadcast a TV show to 1 television set or 1 billion television sets. It still takes the same amount of time. Secondly is we have a perfectly scaling computation on each of the computational nodes of the partial errors for that particular training set. And then we have a log runtime step that gives us the reduction to get the error so that we can then take the next step. So now you see why we can scale out as big as we want to for as complex a data set as we want. And I can go into greater detail for why that's important. But basically, machine learning is a big data problem. You need to give it lots of data, and I'll explain why in a minute. So now I hope you see the path to the exascale and to the future. So we can train fast, we can train big, and the point I always make to students is always report honest flops. A lot of people like to focus on one kernel and say we achieved really high performance. Look at the overall problem. And the key metric for machine learning is not flops, is not iterations per second, it's time to model. So that takes into account the convergence factor, the accuracy of the numerical methods that are also used to find that minimum so that you're not blathering, per the NetTalk example. And instead learning to solve the problem so that you can read aloud or whatever the other problem is that you're interested in. So again, basically straight line scaling. So one of my companies was a bioinformatics company that was acquired by a major pharma. And this is the open example that we gave, which I think you'll find very interesting. So here's Terry's example of taking the text and learning to read aloud is text, going through a neural network and coming up with the phoneme at the top. And for this side, I get to get some exercise up here on the podium. So that's the phoneme. And the reference, of course. And by the way, my slides are available, so all of these have links. So this is what we did with neural networks, is we gave it essentially the DNA sequence, and we said yes or no if it's a exon region or an intron. So then we looked at computational drug design for small molecules. And the closer you look, the greater the complexity, just like when you're learning to design a system to read aloud, if you didn't have the shoulders of giants to stand on like we do now. So if you look at antibody-antigen binding, you know, okay, this is what happens. It's kind of complex. Then you start looking actually more about how the mechanisms work, and it's really starting to look pretty nasty. And then we look at the electron microscope, and good Lord. I'm sorry, it doesn't make much sense to me and what's going on in Mother Nature. She does things beautifully, but she does things differently. So we figured we were going to start our company, so we went and talked to the execs. And they said, you know, we think that you're a bunch of really smart guys, but how do we know that you're not going to be playing expensive computer games with our money? In other words, validation is a key part of machine learning, and it's something that we have to focus on. So what we did is we utilized a blind test. And what we did is I purposely picked these examples because they all look exactly the same. In this case, we took the amino acids for a 6 amino acid length chain, which gave us 20 to the 6 possibilities. And then we predicted the actual binding affinity for the actual antibody. Look a lot like NetTalk in coming up with the value. In this case, we're coming up with a numerical value. Should be really easy to grab, I hope. So what we did is we trained up the network, and we got a really high value, really good accuracy of prediction. Well, that's great. Now we had to do that validation step. So we went to our crazy chemists who made up the compounds. And they said, well, we actually have a data set that we investigated, but it's only 1 to 2,000 examples out of 64 possible million combinations. And they're biased, so they're going to be highly focused around certain parts of that space that we're trying to learn. And so you can have a lot in this region, a lot in this region, and nothing anywhere else. And we wanted to start the company, so we said, give us the data. We trained it up, worked quite nicely, and noticed that that's a very small sampling. Well, what we did is we trained up a model. So you've heard about inferencing, using the neural network to predict, to say yes, no, say it's a dog or a cat or something else in deep learning. Well, what we actually did is we said, we have learned a function that for that particular amino acid chain, we can predict the binding affinity. And so we did hill climbing. And so basically we took one example, modified the last position, found which one was the best, did the same trick over again, pretty easy, found the highest one, and we basically did hill climbing. And we predicted one particular example, which we said was 6 orders of magnitude higher in binding affinity than anything we had seen. And the chemists then went in and made that compound, measured it, and they came back and said, yes, it is actually about 6 orders of magnitude higher. So lesson is first off, don't think of machine learning as just classifying cats and dogs. You can do lots of work with different kinds of problems. So for example, where you use that function, that inference model that you came up with, it's a nonlinear system model that you can use for prediction of other systems. I've actually used it in manufacturing optimization for optimizing pigment loads in plastics to come up with the right color in different lighting situations. So with time series, let's say that we pick from a time series, we take a sample at time t, at constant time t minus 1, constant t time minus 2, so on. Guess what? We're doing the same trick. Except this time, we're now showing it data from a time series. It's wiggling, x versus y. And we predict the time in the future. And same thing. We're learning that function that predicts into the future. Okay? Then what we can do is we can iterate. So we can take the value for time t plus 1, stick it back into the model, and figure out what time t plus 2 is, that value. And we can keep going further and further forward ahead, predicting into the future. It's a nonlinear crystal ball. And guess what? Here's the paper, How Neural Networks Work. And as you can see, the line traces, and we were orders of magnitude better in accuracy as we went out in time on some very complicated problems, basically the magnetic glass equations and the logistic math. So the point is that even in that early work, in the early 80s to 90s, there's a lot of value that we can realize with today's data sets. Okay? Well, here's some work that I did with a good friend of mine, Yanis Krevakridis. He's a professor emeritus at Princeton and is now at Johns Hopkins. And what we did is we actually trained up, we hardwired a Runge-Kutta integrator. And we trained up a netlet to actually be the set of equations that were the model. So here's the Runge-Kutta, and we actually trained up the netlet, and it worked beautifully. We're actually doing more advanced work in this area now. So what you can then do is once you have that system model, let's say you're getting time series data from, I don't know, a turbine, something that's spinning really fast. And what happens is if you get some airflow coming in and bumps it, it can bifurcate. Instead of rotating like this, it can start doing things like this, which is really bad when you're flying on the airplane because basically the seal breaks and the engine falls apart. So you don't want that. The point is that you can take time series data and you can come up with models and you can use these. The other is, how many of you have heard of the cursive dimensionality? I see a couple hands. The idea is that basically we're used to working in a three-dimensional space. Well, as the number of, and we all know who our nearest neighbors are. Dan Olds, who is our video extraordinaire, is sitting there videotaping me, so I don't have any deniability on anything that I say. So, and the quality of the video is due to my friend there. So, meanwhile, the people in the back are much further away. We have an understanding, intuitive view of Euclidean distance, okay? Well, as the dimension goes out, suddenly, as I move to 4 dimensions, there are more people who are close to me, and as I go to higher and higher dimensions, guess what? In one of those dimensions, someone's going to be the closest to me. That's why when you're doing a database query in high dimensional data, you can actually get to the point where you either get no data or you get all the data because everybody's your nearest neighbor. So what you want to do is project that data down onto some sort of a lower dimensional manifold, come up with some way of representing that data in a lower dimension with small error. And guess what? You can do that again. And what you do is you take, say, 1,000 sensor readings, run it through essentially a bottleneck neuron, where we have these bottlenecks. Here I showed it in 3 dimensions because guess what? I can graph in 3 dimensions so you can actually see the problem. So there you can see that over there. And what we do is we run that through and you get X, Y, Z, and we can actually look at the data. So we can actually train up data, high dimensional data, so that we can actually look at it. So it's a visualization tool as well. Okay? So now I brought you from a personal perspective through a few selected items up to then the next desert. And that is around the time of 93, somewhere around there. It's so easy to say, I give this thing data and I get this magic box that comes back and does something for me. I'm an expert. And guess what? Everybody and his brother became an expert in machine learning. And it got to the point where the funding agency said, oh no, you're pitching a project with machine learning. We've been burned on that. Go talk to the guys down the street, maybe they'll fund you. Or the funding agency said, no, we don't fund machine learning projects anymore. And we're at risk at that. I'm seeing the same thing starting to happen because we now have this wonderful thing called deep learning. How many of you have heard of deep learning? I hope, good, okay, a lot of hands came up. So basically what happened is that we've added a lot more layers to the network. Remember that pattern I was talking about is every time we start mimicking what Mother Nature does, we get a big improvement? Well, what Hinton and others did is they essentially modeled the V1 through V5 layers in the visual cortex of mammalian brains, mimicking what Mother Nature does. And amazingly, the networks started to learn to see and to be able to do good recognition. Well, being able to work with pictures and identify pictures and also to do basically sound to text transformations is really commercially viable. So we actually now have a cash cow, a paying pony for making this move forward. And that's where NVIDIA CUDA came in, and we're moving forward, so we're now on the next bandwagon. Okay, so people are now rediscovering all the previous work and being able to run at exascale frameworks. And we're seeing a whole host of problems that you can work with. So here's a list of a few things I talked about from time series and bifurcation analysis. There's other for support vector machines. Huge number of possibilities. Okay, the world is your oyster. It is an exciting time because we have the computational capability. That $30 million connection machine, my cell phone is pretty much faster than that now. So the story I like to use is there was a kid in Finland who wanted to learn virtual memory programming. And so he put out a little operating system. His name was Linus Torvalds, and he changed the world. What I teach in my classes is you have access to teraflop supercomputers. I couldn't get access to one of those until almost 2000, okay? For a few $100s, you can start doing research that 10, 15 years ago was not possible except at the biggest universities. You do have the tools to change the world. You just need to think about it. So this is not an AI history talk, and this is as much for me as anything else because I can talk for hours about the stuff I've just been talking about, and I hope you don't feel it's been that way so far. So anyways, so now we're in the world of deep learning, and like I said, we're entering the era of self-driving cars, but it's just a whole bunch of layers that essentially break up pictures into ways that you can do identification, okay? Well, we're now starting to get hardware to support this. So we're seeing a huge and a wonderful change in mindset, and that is artificial neural networks in physical models. I've been trying to do this for years. And CERN, Sofia Valacorsa and the team at the CERN Open Lab did some extraordinary work using generative adversarial networks. So every time I had a conversation with the modeling and simulation guys, which historically has been HPC, they're going, this is great. You can promise me 3 orders of magnitude faster predictive capability because the inferencing operation is very quick. You can look at complex data and give me this really cool model that will do things. Can you guarantee that you're not going to generate some non-physical effects and put those into my model? I don't know exactly what the neural network's doing, so no, I can't quite guarantee that, at which point the conversation stopped. That's where CERN did, I think, was groundbreaking work that's changing the field for modeling and simulation, climate modeling, a bunch of different areas. And that is that they use a scan. So what they did is essentially had a generator network generate a probability distribution. And then the adversarial network tries to predict if that was from the model or it's from real data. And basically, they train one and then the other, and teeter-totter their way up to the point where if they can't discriminate the generated data distribution from real data. And they actually then verify that separately, of course, with real models from Giant, the kind of the pinnacle of the physics-based models, and they can't tell the difference. So this is allowing CERN to go to orders of magnitude higher luminosity in their simulations to see what they're going to get to, because they can take this neural network module that does inferencing operations 3 to 4 orders of magnitude faster, so they can actually start running simulations on laptops and workstations at these higher luminosities to look at the data and see what kind of physics effects they're going to get. And so they can start verifying the next work before they do this investment. It's a huge, huge, and by the way, did I mention huge change in machine learning? So anyways, here's an idea, some of the data from their work. And basically, the blue and the red lines have to overlap. And just for the purposes of this talk, they do it really well. So it doesn't matter which one you use, as long as it's indistinguishable. Answers that question of how do we know that you're not giving us non-physical effects. And here's the timing. Again, running on a GTX 1080, which is old, is 0.04 milliseconds, and it's 17,000 seconds on a full Monte Carlo. So you get an idea of the speed difference. Start thinking in terms of your own physical models. Okay? We can now also evaluate ANNs for simulation results. Climate is apparently a big thing here. Well, what happens how do you validate your new climate model? How do you know that it conforms to what actually occurs in Mother Nature? Well, what happens is you predict forward. Yeah, it kind of looks like tomorrow's weather. The thing is you've got a whole historical record. So what people are doing is they use their model, start it at the earlier conditions, say 20 years ago, run the model, and what you want to do is see, do I get the same distribution of storms and other events that are not boring to verify the model. Well, the problem is that if you're running 10,000 of these simulations, so you want to get some statistical probability, you can't have people looking at all the climactic events for every day for 100 years of simulated time across all those 10,000 simulations. So what you do is you use deep learning. You use deep learning and you categorize the different kinds of storms. You essentially identify the probability distribution, and bada boom, you've actually got a really nice measure showing that your climate model is reflecting, as the exec said it for our company, you're not playing expensive computer games with our money. You're actually doing real stuff. So again, a big change in high-performance computing. And we're not even talking about the hardware yet. So we can talk about significant hardware and algorithm retooling. Ooh, okay, I need to speed up a little bit. Y'all are being very gracious. So today, the big thing is CPUs and GPUs. Okay, that's the two camps, and everybody goes back and forth about who their favorite thing is. Well, guess what? Tomorrow we're going to have FPGAs and ASIC, data flow devices. And in the near term, one of the most exciting changes, the new pattern of mimicking Mother Nature, is spiking neuron models, which is exactly how our brains operate, all mammalian brains. And we now have hardware, and that's what's made this huge bandwagon possible. We have hardware now coming available for Neuromorphic. And the far-term quantum, it seems ideal for training once we have the qubits, but quantum is basically a big compute, little data problem. Machine learning is a big data problem, so there may not necessarily be a match there. Okay, and so we have all the different frameworks and different camps. So one of the big changes that came out from the algorithmic changes is I wrote an article a long time ago, about 7 years ago, saying numerical precision, how much is enough? Because basically everybody hits it with double precision in HPC and says, that's as good as we're going to get, so that's where we're at. Big deal. Okay, well, Jack Dongarra, not surprisingly, is doing leading edge global research. And what they're doing is they're using the FP16 numerics, and they're actually finding that they can match the precision of double precision for BLAS, like a limited precision BLAS method, that they can match the precision and you're getting a 2 to 4x speed up, which is huge for matrix-based computations. by using these lower precision. So he's actually verifying the precision. More than that is there's efforts called like libxSMM, where they're doing batched precision small matrix operations. So one of the real problems has been in HPC is when you do small amounts of small matrix operations, well, you get serialized on those. And your scalability goes, so you don't add 10 new processors or 10 new cores, you only get a 1x speed up. Big deal. It's pretty much the same. Using the batch methods, you get a 10x speed up because it scales beautifully. So those are two huge changes that are resulting from the current interest by vendors in optimizing for this now lucrative market in machine learning, okay? So libxSMM, that's a good one. HICMA is a project out of KAUST, which I think is extraordinary. You can do million by million matrix operations in gigabytes of workstation memory. Basically, they're doing hierarchical kinds of precision work. So people are starting to study how to do the numerics correctly. Again, low precision played a part in this, and now you can do million by million matrix operations in reasonable time on your workstation, in a workstation with a few gigabytes of memory. So, big change. Directed acyclic graphs. I claim these are going to change HPC in ways that we can't even envision right now. So NLA-FET uses DAG scheduling. Not surprising, Jack and Peter and the team are doing forerunner work. The thing is that they can then use that DAG to generate the scheduling and the code for a destination architecture. I actually use this in my first neural network compiler. And it works beautifully because then you can generate code that runs efficiently on CPUs. You can generate code that runs efficiently on GPUs. Great, we've satisfied all the camps. Guess what? Those new data flow architectures, you can start generating code that will run efficiently on FPGAs. You can actually build ASICs out of those. So it's really, really a wave of the future. And that's built into the library. You can be a user and you still get those benefits. There's no change to the API or to your code. It's just lovely. Okay, we're also seeing a lot of interest in the IoT edge devices. David Keyes, who I think is just a wonderful guy, and the way I describe David is he's so talented it would tick you off except he's such a really nice guy. He and his group have been looking at what's going to happen for future HPC data centers. And basically what we're seeing is going to be part of the data network, not part of the HPC effort. So we're seeing that actually at Argonne National Lab. They've got essentially a data warehouse, and I'm jet lagged, and I can't think of the name of it for the life of me at the moment. I will later. But it's a wonderful thing. Dan Stanzione gave a talk at the last supercomputing about Frontier, the supercomputer. It's going to be the largest academic supercomputer in the US. And afterwards, he said, does anybody have any questions? There was dead silence, and he pigeonholed me, and he said, Rob, I know you've got a question. And I said, okay, well, Dan, I actually am trying to figure out how to ask a question because I never thought I'd use the word agile and HPC supercomputer together in one sentence without a not in between. It's very agile. Basically, what they're doing is they're going data intensive. And, it's the Petrol project at Argonne. Thank you, it's in my notes. But more than that is he's actually using cloud. They actually, when you get your account, you also have an account on AWS. The reason is that the cloud providers are all buying the new hardware, and this way TAC gets applications already developed for the new hardware, and they get codes that are already ready to run, so it helps them with the next procurement. It's really, really wonderful. I didn't have permission to put in here, but what's happening with in storage is extraordinarily exciting. The Intel Optane DIMMs, the DC persistent memory modules, you actually have persistent memory that sits on the memory bus. So you access it from user space. There's no overhead of going through the operating system. It's a direct access, so suddenly your access time for storage is in nanoseconds. And I kid you not, nanoseconds, rather than microseconds. You use something like the DAOS project that's been spearheaded by Gary Greider at Los Alamos and other people who are friends. So I like pitching my friends. But basically, it operates entirely in user space, and it gets rid of all the virtual file system infrastructure for POSIX. I'm seeing heads nodding in the background. So you get rid of all the overhead of the page cache, of system calls, of the block driver, and even of the PCI bus, because it's not sitting on the PCI bus. So you can get that nanosecond access. Suddenly, it's just opening the door for unstructured data analysis. Well, guess what? In machine learning, I don't care what NVIDIA or Intel or any other of the lovely sponsors, thank you, tell you, 90% of the time your data scientists are going to be spending time massaging data. And so you need to think of that when you do your procurement. So basically in the paper How Neural Networks Work, we showed that sigmoid combines together to build bumps. So basically you need a high point where there's a high point in the data in this multidimensional surface and a valley at the right place. The whole game that you play with machine learning is putting data at the right points of inflection. Well, as you get to more and more complicated problems, more and more bumps. As you go to higher dimensional data, more and more bumps. That's why machine learning is a big data problem. That's why the scaling curve that I told you earlier is so important. Make sense? Hope does. And then, of course, there's inference. You can interpolate between the points. Very accurate. Extrapolating is less. So the example I like to give is I got a birthday card that said herpes bathtub, and I'm like, oh my goodness. Okay. And then you open up the card and it said happy birthday. Damn voice recognition. So that's getting the bumps in the right place. Thank goodness people are laughing. So neuromorphic. We're at the beginning stages of this. We're just getting hardware. There's something called the IBM, oh boy, I'm tired. There's also the Intel Lohi project, and I'll think of the IBM project in a minute. But this is from the IBM project. Basically, they showed that they were able to implement deep convolution networks that approach state-of-the-art in classification accuracy. And this is a proceedings in the National Academy of Science paper, so it's good work. The reason why this is so exciting is that neuromorphic computing runs with about 3 to 4 orders of magnitude less power. We use about 10 watts with our spiking neuron model here. Most of these are running in tens of kilowatts to megawatts. So we're going to get to IoT devices. In fact, for really simple problems, we're going to get to IoT devices that are so simple that you might be able to run them off the temperature difference only, say between your wrist and the ambient room. And you can build very big, very efficient power networks. So just like Jan LeCun added a whole bunch of hidden layers, here's a picture of the IBM Synapse project, thank you, with the same neuronal capacity as a rat brain. Literally the same number of neurons. And I don't know how the interconnect is, but reasonably close. So basically, I think we're seeing something towards the future. So going from CPUs and GPUs to data flow architectures to neuromorphic, and data sets, like I said, run between 25 and 275 milliwatts for image classification. Google's got to be very interested in this. So it's easy. Remember that scaling I showed you? This is my Hello World Exascale programming in one slide. Guess what? Y'all will become Exascale capable programmers. Because basically what you do is you print Hello World, and then what you do is some sort of initialization to get your data in, and then you call an optimization function. And over in the green is what runs on your GPU or all the threads on your CPU. And notice that we're just doing a transform reduce. That's it. We're just essentially doing that calculation of the partial errors and then summing them up. And so it runs nicely on a CPU. You can mix the pragmas so that you can actually run with OpenACC, and my second book is on OpenACC, so guess what, plug for OpenACC, to run on the GPU. So what we've seen now is that there is a huge AI convergence. It's impacting all aspects of HPC. It's actually going to impact all aspects of our life. The impacts are on machine architectures and others. There's so much more. You've been really great. I will, since you're being gracious, there's some use cases I'll just flip through really quickly. Is using machine learning to hear gravity in real time from the LIGO project. Converged HPC speeding the path to fusion energy. In fact, I just recently heard about a project where they redefined the pellet that they used to hit the lasers hit the pellet to make it go and turn into a plasma. They actually used machine learning to come up with a different design. The physicists said, oh, we'll just use a ball. Not the best way to do it. The machine came up with a way that was actually able to allow much longer sustained energy output from the fusion. Understanding the standard model, and of course, talking to a scientific audience. Converged HPC, doing drug discovery, work in the medical field is huge. Drug discovery is a big deal. Again, AI monitors Earth vitals for earthquakes and others. Just so many things. So with that, forecasting Zurich fog, y'all are big. That's with Metro Swiss, earthquake, and many others. Thank you. You've been a fantastic audience. I appreciate it. And any questions?